It's a great pleasure for me to introduce Morgan Mitchell from ICFO in Barcelona. Morgan got his PhD in Berkeley at a very exciting time in the group of Ray Chow, where a few of our friends, meaning Paul Kwiat, Ephraim Steinberg, David Deutsch, and so on. Ivan Deutsch. David Deutsch. David was in Oxford, right? So Ivan Deutsch and a few others populated that lab. I think it was an extremely great confluence of people that have, as you know, made very important contributions to quantum physics. And I've been trying to get Morgan for a few years to come, and so I'm really glad that he's here today, and he's going to tell us about the experiments that he and his group are doing in ICFO. Please remember, at 4 o'clock, you will have a chance without the PIs, the professors, to talk to Morgan, all right? So in the JQI seminar room this afternoon, all right? Okay, Morgan.
Okay. Thank you for the very nice introduction. It's a real pleasure to be here. And it's true, you've been inviting me for more than a year to be here. I'm going to be talking about using atoms, cold atoms, to detect magnetic fields in a very sensitive way. And I explained that to our art department, and they gave us this as a representation of using cold atoms to measure magnetic fields. And, well, I mean, it's reasonable. Can anybody in the room say that an atom doesn't really look like this? Okay. There's also something here which is of specific interest to the people that work on weak interactions, because you know that through parity violating effects, you can see whether we're in this universe or a mirror image universe by looking at atoms. And if you look at this particular atom, where north is here, south is here, east is here, and west is here, you can see that at least this atom, and possibly the art department. Okay, so this is basically a quantum optics talk. I'm talking about squeezing. And to talk about squeezing, you need to talk about gravitational wave detection these days. So a gravitational wave interferometer is a detector for gravitational waves. These are disturbances in space-time which come from very far away, produced by very massive objects moving, and they distort space-time in this quadrupolar way, so that space squashes out and comes back. And a Michelson interferometer is a perfect instrument for detecting that because it detects the difference in this arm length versus this arm length. And they've built several of these now, and they're extremely sensitive, so they can measure an absolute difference on the scale of 10 to the minus 18 meters. And when you consider that these things are kilometers long, that's a strain sensitivity, a fractional displacement at the 10 to the minus 23 level. Extremely, extremely sensitive interferometer, which is what you need for measuring these gravitational wave effects, which are very small. Here's some pictures of some of them. So LIGO is 4 kilometers long. The Italian instrument Virgo is 3 kilometers long. I'll be talking especially about GEO, which is a German instrument, which was the first to use a quantum effect to use squeezing in order to improve their sensitivity. This is the sensitivity curve for LIGO. So in 2006, they reached their objective, their first target. Their first target is this black line here, sensitivity as a function of frequency. And you can see that it reaches these incredible strain sensitivities. And you can also see their different regimes. This regime is limited by shot noise. There's a low frequency region where it's limited by seismic noise because it's difficult to keep objects that are separated by 4 kilometers from moving relative to each other. And there's an intermediate regime which is limited by thermal noise. And the idea of the squeezing is to improve the sensitivity in this region. You note that these frequencies are reasonably high. So this is about 150. The highest sensitivity is at about 150 hertz. So is there something which is in the universe which is oscillating at 150 hertz? And the answer is yes, there is. This is Okay, that's too bad. This is a supercomputer simulation of black holes orbiting around each other. As they orbit, they radiate distortions in space-time and they lose energy. And as they lose energy, they move closer to each other and they speed up. And as they speed up, they radiate more and more energy until finally they merge into a single black hole. And you can see this is a plot of the strain which would reach Earth from a coalescence of two black holes. And so you see this, this oscillation which is chirped, so it gets faster and faster and faster until finally in a burst it gives up a huge amount of energy. This is the most energetic event that people think is happening out there. So here's a paper where they reported on a couple of years of search with the LIGO and Virgo instruments looking for this process of in-spiral merger and ring down. This again is the strain as a function of time. Here's the list of authors. Small collaboration. When I look at this strain and frequency, then it has these high-frequency components in it because this process is extremely dynamic. And when I overlay that with the LIGO sensitivity, then I see something which has a significant amount of signal in the shot noise limited region. So that means that improving the shot noise in this instrument makes it a more sensitive instrument for detecting these kinds of events. The idea that you could use some sort of quantum effect to improve the sensitivity goes back to 1981, so when Carl Caves first proposed this idea. So he did an analysis of these kinds of interferometers. So this is a Michelson interferometer, and everybody knows that you send in a laser field and it splits into two, and then what comes out here has two contributions which can interfere constructively or destructively. And I think prior to 1981, everybody thought that this was a correct description for the average signal that you would see, and then on top of that, there was a quantum effect which was shot noise. And the idea, I think, was that the average signal was given by the wave properties of light, and the shot noise was given by the particle properties of light. And somehow Bohr had said that these things were fixed in this way, and there was nothing you could do about this. And then Caves, in 1981, gave a different analysis, where he suggested that this should be something which we can actually play with, and we can beat the shot noise. So in Caves' analysis, he notices that there's something missing from this picture, that in fact there's a field which enters in here. It's also going to split into the two arms and come back out and give us some other output here. Okay? And then now we've got two things coming out the same port, and not only is there an interference of these two paths, but there's an interference of the laser field against the vacuum fluctuations. Okay? And quantum field theory tells us that these vacuum fluctuations are something which is random, uncontrolled, and so when you interfere that against your nice clean laser signal, then you'll get this oscillating noise, you get this noise, and that's what's responsible for the shot noise in this kind of interferometer. And then with that analysis, he goes on to propose a cure for the shot noise in these gravitational wave instruments. So here's the gravitational wave instrument. There's a laser which is feeding into it. And here's a squeezed state, which is coming into the unused port in order to change the quantum noise of the vacuum, which is limiting the sensitivity of the instrument. Okay, to generate the squeezed state, he has a couple of things. He has a frequency doubler, and he has a parametric amplifier. So I'll explain a bit more what those things are. So, a parametric amplifier, also known as a sub-threshold optical parametric oscillator, is a nonlinear optical device which is powered by a pump laser and uses a nonlinear crystal in order to cause a phase-sensitive amplification. So in particular, for a given frequency, there will be one quadrature, the cosine component or sine component, that is amplified and one that is de-amplified. Okay? And so if you put that inside a cavity where you have one mirror which is leaky and the other are not, then vacuum fluctuations can enter and they can be amplified in this phase-sensitive way, and then after several times through the cavity, they'll come out in a squeezed way. So why is this? It's because the cosine component, this, has been amplified, and the sine component has been de-amplified. And if you imagine interfering that against your laser, then you can see that if the phase, if the peaks of the laser correspond with the peaks of the noise here, then you'll have a lot to interfere with, and you'll be very noisy. And if they don't coincide, then you can be less noisy. So there's your noise is now a function of the phase between the laser and the squeezed vacuum that you're sending. So here's a diagram of an instrument from my laboratory. So we have a diode laser, which is tuned to the rubidium D1 line, so it's stabilized. And then we amplify it, frequency double it, so we have some blue light to use as a pump. And then we have a parametric oscillator here, which is based on the nonlinear crystal PPKTP. And then vacuum fluctuations enter here, and they circulate several times. And here we get squeezed vacuum coming out. Right? We also have a bit of the laser, which comes in here, and that goes into this. This is a polarization interferometer, so you can see that there's the laser enters, and then at the end it's split to two detectors in function of the angle of this wave plate. So that's analogous to entering the Michelson and being split in function of the phase of the two arms. And so we're going to inject squeezed vacuum into this unused port, and that will change the interference conditions here at the end and reduce the noise of this interferometer. Okay, so if we look at the noise on a spectrum analyzer, then we can clearly see this. This is with the squeezer off, this green line, and with the squeezer on, we see as a function of phase, so as time goes by, we're sweeping the phase, we can see that it's less noisy or it's more noisy as expected. You can also see this in time, so this is with the squeezer off, and this is with the squeezer on, again, as the relative phase is changed. So I can play for you here. This is the shot noise. Which is about the most boring signal you can imagine. And then this is the squeezing. So you can hear, this is not something that you need a sensitive electronic instrument in order to detect. This is something that you can perceive directly. I also tell my students that if they're thinking of going to the beach, then they can instead go to the lab and do this experiment. And
so how many dB is squeezing?
That's very, very little. This was, I mean, we didn't have it running very well. We just wanted to observe it. So you can see that it's the difference between this, which is the shot noise, and this. So that's we do much better than that.
Sure.
Okay.
But what we were hearing, how much dB, how many dB was it between the highest noise and the lowest noise? I'm just trying to calibrate my ear.
Yeah, so I think that's about 3 dB between the anti-squeezing and the squeezing. Okay, so this idea, this has been the first squeezing of this kind was done in 1985, and people have gotten very, very good at it now. So in preparation for applying this in gravitational wave instruments, people built these prototypes. So this is one that was built by LIGO. This is a real but small gravitational wave detector fed by a laser, which is cleaned up by some optics here. And then this is the squeezing generation, that there's a second harmonic generation and a parametric oscillator to generate the squeezing. And then that's fed backward into the unused port of this instrument. And you can see here what you get. This red line is the shot noise curve, and then with the squeezer on, it drops below. An important thing here is that they wiggle one of these mirrors, and they can generate a fake signal here. And you can see that the signal to noise improves. So the signal is the same, whether it's squeezed or not, but the noise changes. Okay. And then finally, since the end of 2011, the GEO 600 instrument is running with a squeezer in regular operation. So it's running now, it's doing gravitational wave searches now, and squeezed light is making it more sensitive. As you can see here, again, is the unsqueezed and squeezed sensitivity curve for GEO 600. There's a lot of activity to apply this to atomic instruments. So atomic clocks, optical magnetometers, gyroscopes, other interferometers. I'm working with magnetometers. That's very active in recent years. So here's a list of papers where some sort of quantum effect was used to improve the sensitivity of a magnetometer. And I'll be telling you about these two from my group, where we squeeze light and then we squeeze atoms in two different experiments and improve the sensitivity of magnetometers. An optical magnetometer, it consists of a sensor, which is an atomic ensemble. It's a collection of atoms. They each have an individual spin, but we're interested in their collective spin, so the sum of the spins of all of the atoms. And in the presence of a magnetic field, that somehow acquires a component, which is along the axis. And now we have the conditions for Faraday rotation. That is to say, linearly polarized light comes in, and it gets rotated. And that's something we can detect directly with a PBS and a balanced detector. This technique is very successful. So for low-frequency magnetic fields, this is the most sensitive technique for detecting magnetic fields. So in 2003, the Romalis group demonstrated a technique which was, for the first time, more sensitive than squids, and they continue to improve on that. So these are numbers better than a femtotesla per root hertz, to give you some sort of scale at the extreme high sensitivity end. There are miniaturized versions of this. So NIST Boulder has developed these chip-scale magnetometers. So here's a laser and polarization optics and a cell containing an atomic ensemble, magnetic field coils, and the detector. And this whole thing is the size of a grain of rice. So you can put a very sensitive magnetometer in tiny instruments. And then it has applications in a number of different areas. It turns out that both the heart and the brain produce enough electrical current that there are fields that you can detect outside the body, and in that way do a non-invasive monitoring of body processes in real time. Okay. If the other video didn't work, this one isn't going to work either. And I'll just say, this is a commercial instrument made by a Finnish company. Inside here, there's a cryostat so that they can have a collection of squids. So there's a helmet of squids. The patient puts their head in here, and then it can detect the fields which are coming out of the brain. Okay? And so this sells for about €1 million. There are somewhere around 500 of these in the world, and they exist in hospitals, for example, for detection of epilepsy, but also for scientific studies. And one of these scientific studies is so mind-blowing, if you will, that I can't resist telling you about it. So this was done by a group at Cambridge, published last year. And they took Cambridge students and they put them in this chair and they played sounds to them, which were either real words, like boat and joke, or they were fake words, like boke and jote. Okay? And the difference between these in some, they have the same sounds in them, but these ones mean something and these ones don't. Okay? And you can't tell until the last sound whether it's a real word or a fake word. Okay? So this is a way to test how long it takes your brain to recognize that it's heard a real word. Okay? So the last sound, they call that time zero, and this black curve is for the real words, and this dashed curve is for the fake words. And you can see there's no difference before time zero, because there's no information about the meaning there. And then as little as 50 milliseconds later, you start to see a significant difference. And you can also see that the difference, is located in a region that's very close to your ears. Okay? And so your brain is so optimized that the part of your brain that first recognizes that it's heard a word and not just some sound is close to your ears, because that reduces the travel time for a signal to get from the sensor to the processor. Okay? This here is a femtotesla, and so you can see the need for sensitivity in these kinds of experiments. Okay. Okay, so enough advertising for magnetometers. Can we do LIGO or GEO for magnetometry? Okay, so we take our squeezing setup and we put in here, inside our polarization interferometer, we put a rubidium cell, and that's going to be our magnetic sensor. The sensor is about as simple as we could make it, because this was the first experiment that used squeezing in this context. So we have a rubidium-87 cell. There's nothing else in there. It's just vacuum and rubidium-87. It's anti-reflection coated to preserve the squeezing properties of the light. It's inside a coil so that we can apply a calibration field, and inside shielding. But this is about as simple as we could make it. The probe laser and the squeezing are tuned about 2 Doppler widths to the to the blue of the 2 to 2 transition. This is on the D1 transition. And the atoms were just left in their initial unpolarized thermal state. And so this is about the simplest magnetometry situation that you could imagine, or that we could imagine. It turns out that, and okay, it gives a signal. The mechanism is something which is called nonlinear Magneto-Optic rotation by alignment to orientation conversion. And this is a known technique. This is something which is used in optical magnetometry, and it has some advantages. So, for example, you can avoid some deleterious effects. So, what does it mean? Orientation is spin polarization in the way that we usually think about it. So, if there's more in one state than in another, and alignment is what we would normally call in this community Raman coherence. So coherence between non-adjacent bubbles is what's in magnetometry called alignment. So this is going to be a technique which turns alignment into orientation as part of the signal generation. Okay, so here's a cartoon version of how this works. We have a continuous beam, but we can understand the process in steps. We start with a completely unpolarized ensemble, and then the presence of the probe beam optically pumps into a dark state here, which is to say it produces a coherence between all of these states. That generates alignment, because this is a Raman kind of coherence. Then, in the presence of a magnetic field, that coherence gets rotated. Okay? And so now we're not exactly the dark state, and so the probe can cause something else to happen, which is stimulated Raman transitions. And now we've converted our alignment into orientation, and that orientation means that there's a spin polarization, and that's experienced by the probe as a Faraday rotation. Okay? So this is about as simple as it gets, which is to say not very simple. So we wanted to see if we can improve that with squeezing. So here's a sensitivity curve without the squeezing applied. So you can see this is the shot noise level, so it's very flat. And then there's this spike here, which is an applied signal at 120 kilohertz, and there's some small technical noise here, which we never figured out what it was. Now we turn on the squeezer. We add one more thing, which is we add what's called a quantum noise lock to stabilize ourselves at the phase which gives the minimum noise. Okay, that's necessary, just because we want to remain at the minimum noise. Okay, and we see this. So this was without the squeezer. This is with the squeezer, and we can see a 3 dB improvement in the sensitivity of the magnetometer, and we see also that the signal to noise improves. We can also tune away from the atoms and do the experiment with no effect from the atom, and we can see that the squeezing that we had available was about 3.6 dB. So it's pretty efficient with the squeezing that we're using. Okay, so that was 2010. there's a paper which just came out from the group at William and Mary, where they did something which in some ways was similar. So they used a magnetometer. For squeezing, they did something extremely simple. They just have a laser and a cell here, and by optical self-rotation, this generates polarization squeezing. And so there's a potential here that you could have, compared to the miniaturized versions, this is just one more cell. So you could put this into one of these miniaturized magnetometers and get a squeezing advantage in a device which is much simpler than what we have on the table. They didn't get quite as much quantum advantage, but they also got more sensitivity, so it's not it's a multi-dimensional thing. Okay, so now I'm going to switch to squeezing of atoms. This is going to be a lot more technology and probably a lot more physics. So our cold atom magnetometer looks like this. We load atoms from a 2D MOT into a 3D MOT and then into an optical dipole trap. And once they're in the trap, then we can turn off the MOTs, and then we have an ensemble which is optically trapped and is very, very clean in terms of its spin physics. Then we probe it, so we have probe inputs, a couple of them, which are overlapped with the dipole beam. And that allows us to probe really along the axis. And then again, we have a polarimeter here, so a shot noise limited polarimeter for measuring this Faraday rotation. We have optical pumping from a couple of different directions, and then absorption imaging, which is useful, for example, for measuring the number of atoms. The absorption imaging gives you some idea of the geometry of the trap. So this is about 8 millimeters long and 20 microns in width. So we have an extreme aspect ratio for a trapped atomic sample. And that's nice because it means that each photon that goes through, in some sense, hits all of the atoms. So it can get a very good optical density from a small number of atoms. So we trap about 1 million rubidium-87. They're cold, they're not condensed. We almost always work with the F = 1 ground state, so that's our spin system. It's an F = 1 system. And then we probe it with pulses that are about a microsecond long, linearly polarized at the input, and then we catch them at the output and see what their rotation is. This probing is non-destructive, as you can see here. So here is the number of probe pulses so we polarize the atoms, so they're completely in one of these states. And then we probe them several times, and we see a rotation which is as large as 100 milliradians. And you can see that we can probe them hundreds or thousands of times without destroying their spin state. Okay? And more so, we're not destroying the atomic ensemble. So this is something we can repeat many times. Here's a use of this as sort of a utility magnetometer. So this is something that we use daily to know what our magnetic field is. So we first optically pump the atoms into some direction, say along the axis here. Okay? And then in the presence of a magnetic field, the spin is going to precess around the magnetic field, and we can probe it. So here we probe it every 10 microseconds, and we get to see this free induction decay signal. Okay, and that gives us some information about what the magnetic field is. For example, the frequency here tells us what the magnitude is. And then we optically pump in some other direction, and we probe again. We get another free induction decay, and putting these two together tells us the direction, the magnitude, and one gradient component. Okay, so we get a lot of information from this kind of measurement. This, for example, is our 50 hertz field in the lab, so the 3 different components as a function of time. And so you can see we don't have a particularly clean field. We've got micro-Tesla fields fluctuating, but they're pretty predictable. So the uncertainty on one of these points is small. And we can do even better than that, since we can repeat this every millisecond without having to reload the trap or anything, we can measure here and try to predict what the field is 1 millisecond later.
Okay, so why don't we see your field in
Well, because we canceled that with coils. So, I mean, it's a trapping experiment. We do what we can for the DC fields, but for the AC fields, it's not so well controlled. Okay, so measuring at one point in time and trying to predict a millisecond later. So that's shown here in a correlation plot, that this is the first measurement, this is the second measurement, and you can see, for example, here, this is the X component of the field. There's a large variation, but it's predictable. So based on a measurement in this cycle, I can predict 1 millisecond later what it's going to be. And so using that kind of information, we can get our uncertainty down to about 9 nanotesla. Okay, so that's somehow a number of the residual noise that we have in the experiment. So now, how would we improve a magnetometer like that using squeezing? So first, what does it mean to squeeze atoms? So we have this collective spin. So it's a large spin. It's a sum of spins, so it's still a spin. And it's going to obey spin commutation relations, this and cyclic permutations, and that implies spin uncertainty relations. So for example, this. Okay? So that means that if we polarize all our atoms, say along the y direction, then there's going to be an uncertainty in the x direction and in the z direction. And this is something that we can take as a starting point. And this is referred to as a coherent spin state. But there's also the opportunity, we could reduce this component as long as we're willing to increase this. I mean, reduce the noise in this component as long as we increase that. And that's called a spin squeezed state. And this is what we're talking about when we talk about squeezing of spins or squeezing of atoms. And this is a very attractive idea for magnetometry. So imagine that you have some spin and you're wanting to watch it precess. Then you would be measuring this in, say, as we do, every millisecond, and seeing how it precesses in response to the magnetic field. Well, if this measurement is good enough, then you measure this Z component and you get some information about it. So now, after the measurement, you know what it is, possibly, if your measurement is good enough, with an uncertainty which is less than the standard quantum limit, which is less than the uncertainty of the coherent state. Okay? And so that will collapse your state down to something which is squeezed in this direction, and somehow it must become anti-squeezed in this direction in order to stick with the uncertainty relation. So it means that just by doing this precession measurement, you would be generating squeezing, and every time you measure, you become more sensitive in the next measurement. The uncertainty here is determining how well you can interpret the result of the next measurement as a rotation angle. Okay? So this idea was proposed by Alex Kuzmich using a spin 1/2 model, and it's been implemented in a number of different systems. And you can see almost all of these are spin 1/2 systems, and only one of them is a magnetometer. The magnetometer result came from Hideo Noguchi's group. It was published in 2004, 2005. You can see here the uncertainty relation. This was an important experiment. This was groundbreaking. This provided a lot of important information about how to do these kinds of experiments, but it didn't actually work. So they retracted these results. And so as of last year, there was still no spin squeezing in a system that was not spin 1/2, and there was no spin squeezing in a magnetometry system. Okay, so we now have spin squeezing in a magnetic ensemble, which we published in December of last year, and I'm going to tell you very, very briefly how we did that. We've been working on this since the retraction by Noguchi group, and so it's going to be a bit brief. Okay, okay, so first, we have this collective spin that describes the atoms. To describe the light, we want to describe the polarization. We do that with the Stokes operators. So these are observables, difference of photon number in different bases. And they're also, if you calculate the commutation relations, they also describe a macroscopic spin. So we have two spin systems which are interacting with each other. The Faraday rotation in this language, the rotation from something which is X polarized toward 45, which is Y polarized, that's described this way, that Y acquires a component which is proportional to X, that's the rotation, and its rotation angle, which is proportional to Fz, the longitudinal component of the spins. So the first thing that we need to do, is to show sensitivity, and then we need to deal with the spin, the fact that it's not a spin 1/2, and then we can finally do the magnetometry. Okay. So given this rotation physics, we want to know the sensitivity. To do that, we borrow a trick from quantum optics. So you probably know that in quantum optics, shot noise scales as, if you look at the variance of a signal, or the power of a signal, the shot noise scales as the number of photons that you send in. Whereas your electronic noise has nothing to do with the number of photons that you send in. And that allows you to identify the shot noise from just a signal by scaling with the size of the system. Well, the same thing is true when you're talking about atoms. So here we have electronic noise, shot noise, technical noise for the light, and this is the atomic shot noise. So it's something which is proportional to the number of atoms. And then there's a technical noise for the atoms, which goes as the number of atoms squared. And we can extract all of these by doing an experiment where we prepare a reference state. This is, again, an unpolarized state. It has a known single atom uncertainty for this component that we're measuring. And then we measure this total noise as a function of the size of the system, where the size of the system now has 2 dimensions, number of photons and number of atoms. So we prepare a thermal state, we measure this Fz component using some number of photons, and then we measure the number of atoms, and then we repeat, and every time we prepare, we lose some atoms, and so this way we get the noise as a function of both number of atoms and number of photons. And this is something that we can fit with that polynomial, and we get to sort out what the contributions of different components are. So this is what we get at our largest photon number. So we get a system which is dominated by the atomic noise. The next largest component is the light shot noise. And so we have a system which is quantum noise limited in both the atoms and in the light in the system, which is what we need in order to do the spin squeezing. Okay, so next, why didn't this work with a spin 1 system? So first I have to tell you why it does work with a spin 1/2 system. So spin 1/2 system, it's an SU2 system. To describe it, I only need the 3 spin components. Okay? The Faraday rotation is described by a Hamiltonian like this, and that describes the light shifts that are caused by these 2 circular polarizations acting on these 2 ground states. Okay? And then there's also the magnetic field. This interaction Hamiltonian, from the perspective of the atoms, that means a rotation about this axis proportional to this Sz component. From the perspective of the light, it's a rotation about this axis proportional to Fz of the atoms. Looking at how these 2 act, so first, the Fz component here is uncertain. That means the rotation angle here is uncertain, and that causes a broadening of the atomic state. At the same time, the atoms are causing the light to rotate, and then we measure it immediately afterward. So if what we see is that the light rotated in this direction, that means that the atoms must have had a Z component in this region. Okay? And so through this mechanism, we get the squeezed state that we wanted to see. We reduce the uncertainty here by measurement, but there's a back action which increases the uncertainty here. Then in the presence of a magnetic field, that will evolve, and the next QND measurement will squeeze it again, make it more sensitive, but also tell us how far it evolved. So this works beautifully in spin 1. What happens with spin 1? Well, spin 1, we no longer have 2 levels here. We have 3, and now we get some new physics coming in. So in addition to the light shifts, we get Raman transitions. And these are described by the tensor polarizability here. So these are additional terms in the Hamiltonian. where these J's are alignment components. That is to say, they are coherences between these two states. So mathematically, those are described by single atom operators that look like this, by collective operators that are the sums of those. And surprisingly, these, we have now two spin systems. So fx, y, and z, and jx, jy, and fz. And so the alignment, the Raman coherences here, rotate in response to fz in the same way as coherences among these three, which we describe as the polarization. Okay. So what happens now? Well, this is what we wanted to have happen, but at this step, where we're supposed to be making the QND, we now have this extra term in the Hamiltonian, Jx Sx, that describes a rotation about this Jx axis proportional to Sx. But Sx, that was our input polarization, that's large. So this is a significant rotation angle. And what it does is it rotates Jy into Fz. So Fz is what we're trying to measure. Jy doesn't seem to have anything to do with the problem, and it's got a quantum noise in it. So we're just coupling some environment variable into our system, and that's what spoils it. So this was understood by smart people. John Stockton was a graduate student in Hideo Mabuchi's group, and he understood this. Paul Jessen understood this. We had to discover this in experiment, which was always the hard way. But we did discover it. And what we see is exactly what I said, that if you probe with one polarization, then you get a coupling, a rotation about this x-axis. If we polarized with the opposite, if we probed with the opposite polarization, then we would see a rotation in this direction. And our solution to this, which is extremely simple, is just to alternate probings back and forth. And so the system makes a rotation up in this direction and then back in that direction. Okay? And in that way, we can decouple Fz from Jy. Okay? So this is a dynamical decoupling, which turns this into effectively a spin 1/2 system. Okay, so we've done that. In this process of dynamical decoupling, the atoms make a rotation up here and then back. Okay? The light, however, is always being rotated in response to this component Fz. The result is that some bit of Jy ends up in Fz even temporarily. So during the probing, it's there. And so the signal that you get is actually responding not to Fz, but to some combination of Fz and Jz, which we call K. Okay? So what we're measuring is actually a linear combination of Fz and Jy. Okay. So now that we understand that, we can do a spin squeezing experiment. We collect our atoms, we pump into Jx, we measure Jx. This tells us how many atoms we have and how much coherence we have. We pump into Jx, and now we do a QND measurement followed by another QND measurement. And if this is working, then we should be able to predict the second QND measurement based on the first one better than the atomic shot noise. We can see that. This is the first measurement versus the second measurement. And you can see that they're correlated, so that knowing one tells you what the other one is, still with some noise, but that noise is below the standard quantum limit, which is indicated by this circle. In contrast, if we take first and second measurements from different preparations of the ensemble, then we see something that's uncorrelated that looks like this, and that matches the standard quantum limit. And this is if we take the atoms out of the problem. This is just our readout noise with the optics. When we make that quantitative by looking at the conditional variance, that's this orange stuff, that's the remaining noise after the prediction, we can see that the first measurement and the second measurement by themselves fall very nicely along the predicted shot noise level, and we have about 2 dB of squeezing. We have about 3 dB of squeezing relative to that in the conditional variance. And when we include the coherence in the calculation, we have about 2 dB of Wineland criterion squeezing. So this is a metrologically significant amount of squeezing. Okay. And then finally, we do a magnetometer with that. So we start with this polarized state. We do a QND measurement that gives us something squeezed that rotates in response to a magnetic field. And then the next time that we measure it, we get, since we're measuring along this axis, then we get a part of the rotation in here as signal. Okay? And meanwhile, our noise is entirely coming from that component, and so it's squeezed. Okay, so the sequence looks the same. In fact, it's the same data. Just we're looking at the noise of just one of these measurements, and that is our measurement of the field by alignment orientation conversion. And this is what we see. If we use a coherent spin state, then we see this as noise versus the number of atoms in the system. And with the squeezing, then we can see something which beats that, not by very much, by about 1 dB. Note that there's no noise subtracted from this. So this is the noise of the magnetometer, whereas this is the noise just from the atomic state. I should have said that this has the optical noise subtracted out of it, whereas this does not. And you can see a bit what's happening here, that there's the light shot noise. This is the spin projection noise that we would have if there's no squeezing. So the sum of these two things gives us this blue curve. And with the squeezing process, we get a squeezed spin noise, which is now dropping, and that gives us this red curve. So we have a little bit of squeezing. We have a significant amount of squeezing in the atoms. It produces a smaller amount of advantage in the magnetometer, basically because we don't have enough atoms. So when we did this experiment, our trap was not working as well as it is now. We could now have about 2 times as many atoms as this. So that's it. There's more to say about this, but I think I will not go into that today. So I will say I've shown you noise reduction in the magnetometer using squeezed light. I've shown you noise reduction in the magnetometer using squeezed atoms. There are some interesting things to say on the outlook. I think I'll leave that for questions. And I want to finish by describing this. So Sheldon Briner is the Indiana Jones of optical magnetometry. He worked for Varian Corporation, and so he was in Palo Alto, and he developed applications for magnetometers, for example, looking for minerals in the ground. And for fun, he would go and explore places with magnetometers. And he has this fantastic website where he describes all of the things that he has discovered using magnetometers. And this is just one of them. Here he is in southern Mexico in a field. This is a cesium-vapor magnetometer, which he's holding at a distance from him so that the magnetism of his clothing and things like that doesn't disturb the measurement. And he maps out the Earth's magnetic field, which looks something like this in this field. And so he determines that there must be some large magnetic object here, and he pays some guys to dig a hole here, and he finds this. And this is a colossal head made by the Olmec civilization a long time ago, about 1,000 years ago, I think.
3,000.
3,000, sorry. So 3,000 years old, and he has found several of these. I think he's found about 5 of these. Personally, just walking around in fields with magnetometers. So magnetometers can make other kinds of contributions as well. So I would like to thank the people who did the work on this experiment. These people did the optical work. These people did the atomic work. And I would like to thank you all for your attention.